All right, in this module, we're going to work through an example of an extrinsic defect reaction. All right, so what I want you to look at, and this will be in the quiz, is I want you to write a defect reaction for a sodium chloride crystal with impurity amounts of potassium chloride in it. So see if you can write the complete defect reaction balanced in all the ways that we've talked about before. Do that, put it in the quiz, and then we'll come back and we'll discuss the results. All right, let's take a look at the example that you worked in the quiz. So sodium chloride crystal with potassium chloride impurities. So we want to look at the defect reaction for this. So we're adding in this component, right? And so in this case, we actually write that on the reactant side. And again, we could write in that sodium's in the sodium site and chlorine and that, and so forth, but we don't need to write that here. So we'll just put Cl or KCl on this side. And we know that in this case, cations tend to replace cations, anions tend to replace anions. And so in this case, we can write that the potassium is going to take the sodium site, right? Those are the cations. And the charge, right? This is plus, this is minus, plus, right? So the charge works out to be null or 0. And if we add in the Cl for Cl, that's the same, right? And so there's no charge balance here. So this would be if we replace the host crystal with these potassium chloride impurities, right? The impurity dopant goes into the nearest or most similar electronegativity, so potassium and sodium, and chlorine's the same. And again, we can write, if we wanted to just really make sure we are aware of what's happening, we could also on this side put that the sodium is in the sodium sites initially and the chlorine in the chlorine sites initially. So we could also, add that there if we really wanted to. All right, so that's really all there is to it in this case, right? Because this is a pretty straightforward example because the charge is the same, right? Now, however, let's look at a different dopant. So we're going to look at the same crystal, sodium chloride, but then we're going to add the dopant this time is going to be CaCl2, so calcium chloride. So just like before, right, cations for cations, anions for anions. So if we do that, we could again write this as our dopant going into the structure. And so calcium is going to take the sodium site. And in this case, this has a +2 charge, right? And this has a minus. And so the replacement of this is going to be a net +1. We still have to account for the chlorine going in. And here's the, when we have this, both of the chlorines have to be accounted for bookkeeping purposes. So if you see 2 over here, you have to replace it here. So Cl is going to go for Cl, and there's going to be 2 of them. And the charge is no charge on that. However, it's not balanced now, right? We have no charge here associated with this, but we have a net charge here when we're talking about calcium, because we've essentially removed sodium and replaced it with something with a higher charge. So in addition, to balance this, what we need to account for that, and if we can get one way we can get that, maybe the most straightforward way would be to think about calcium coming in, one of those, and replacing 2 sodiums. So effectively having another vacancy of sodium, because this would then have a negative charge. So effectively, the calcium's taking one site and also leaving behind another vacancy, and the charge now balances. So in this case, that's how we're balancing it. We have the additional cation balances two sites here, and then also creates a vacancy for this, right? So this is if cation replaces cation, anion replaces anion. We could also alternatively think of a slightly different approach. Is if we have calcium chloride, and the calcium goes for sodium, and we have chlorine go for chlorine, but we only have one of those, and another chlorine goes into an interstitial, which would then create the negative charge to balance, right? And so this would have to be weighed for this particular crystal with the relative size of the chlorine anion. So that's the reason why this may not work. It's just kind of another way we could write it, but it really depends on the relative size of our ions. And this would give us no vacancy like we had up here to do that. So this is kind of an alternative approach, but again, it's difficult to determine which one of these would be. We can make some predictions based on the size, since it has to have an interstitial, but for a lot of these cases, you might need an experiment to determine which one would in fact be true.